All right. So, first of all, let me make an announcement. I don't think I've officially said this yet. The final exam is a week from today. Next Monday, which is the 28th. And it's scheduled by the registrar to be from 8 to 10 a.m. Now, this is not a multi-section course, and this is not in the time that we usually meet. And I presume that most, if not all of you, will be taking the exam remotely. So, I propose that we just have the exam at our normal meeting time, 1:30 to 3:30. It's a 2-hour exam. And there'll be an additional 15 minutes for uploading time. Now, I understand that this might be a problem for some other of you who may have an exam scheduled later that day. So, let me just write down. Proposed rescheduling of time. I'll send out a survey this afternoon to see if that works for most people, and if not, maybe we can find a time better than 8 a.m. Or if not, we can stick with the scheduled time, 8 to 10. But I really want your feedback on that. I'm presuming most people would not want to take the exam at 8 a.m. If I'm wrong, well, then please let me know. Okay, furthermore, okay, so I'll just say, survey on Canvas. Furthermore, let me just remind you, let's say, also this afternoon, I'll release some practice final exams. And this afternoon, with solutions to follow on Wednesday. Okay, so just as a reminder, of course we have an exam tomorrow, exam 4, and shortly we'll perhaps go over some questions for a little while about the practice exams from exam 4, and we'll also do that tomorrow before the exam. But I just wanted to remind you, we kind of have our schedule laid out for this week, and it's pretty tight, of course, right? So today we'll do a little bit of exam 4 review, followed by finishing up section 11.1. Then tomorrow we'll do a little bit of exam 4 review in the first 30 minutes of class, and then, or 40 minutes of class, as it may be, and then we will take the exam, and then on Wednesday, we will go as far as we can in the classification of wallpaper groups. Okay, I'll at the very least tell you what they all are. That is to say, we'll build the machinery to make the classification today, and then at least outline it on Wednesday. Keenan asked about exam 3. I'll release those tonight. I'm sorry that it's taken me so long to get that done, but yeah, they'll be out tonight. Okay. So and then on Thursday, what we'll do is just spend the entire class period reviewing for the exam, the final exam. Thursday, final exam review. Okay, so that is to say, contrary to the syllabus, we will not be covering anything from chapter 12. Okay, there simply just wasn't enough time. I'm sad to say. Yeah. So I think that covers all the announcements I wanted to make. So what, if any, questions do we have about the practice exams for exam 4? I believe I sent out one from 2014 and one from 2018. Do we want to talk about any of those yet? Okay, so Keenan asks on 2018 number 2, how do we determine what kind of isometry this is? Okay, so the first, and I understand why it's not really clear from the solution what's going on. So let's just run through this. Hello? So at the very top of the solutions, right, there's these curly braces that say the coefficients of x prime are a equals 5 over 13 and b equals 12 over 13. And then what you notice is that the coefficients in the equation for y prime are a and b swapped and the sign of a flipped, right? So if you refer to the theorem in chapter 9 that gives us the general equation for an isometry of the plane, right? There's we have this characterization of when an isometry is even or odd, right? That is to say, if there's a sign flip, so it's theorem 9.2, right, in the textbook. If there's a sign flip in the coefficients from x prime to y prime, well, let me just recall the theorem for you. So this is number 2, 2018. So recall an isometry has equations x prime equal to ax minus by plus c, and y prime is equal to bx plus ay plus d. Oh, I'm sorry. I skipped the most important part. This is plus or minus plus, if even, and minus if odd. Okay? So that is to say, since the signs flip on the coefficients between x prime and y prime as given, we know that it's an odd isometry. Right? There's this negative sign in the equation for y prime. Therefore, since it's an odd isometry, we know it must be a reflection or a glide reflection. Right? So, what's the most effective way to tell the difference between a reflection and a glide reflection? What is the salient property that distinguishes these two types of isometries? Yeah, good. Thank you, Jordan. Fixed points, right? So, in order to have a fixed point, we replace x prime with x and y prime with y. So let's just record this quickly. So this implies either reflection or glide reflection. Okay, so then we check if it has fixed points. Right, and of course the reflection fixes a whole line pointwise, i.e. the line that it is a reflection in, and a glide reflection has no fixed points. Okay, so just to reiterate what I was saying, a fixed point x comma y satisfies x equals 5/13 x plus 12/13 y plus, minus 1, and y is equal to 12/13 x minus 5/13 y plus 2. So in other words, we have a system of linear equations, right? And in fact, just by doing some good old-fashioned algebra, we get to 8x minus 12y is equal to negative 13, and 12x minus 18y is equal to negative 26. Okay, so if you just try to solve this system of linear equations, you'll quickly find that it's not solvable, right? So what does that tell us? If a fixed point satisfies these equations, which are equivalent to these equations, and these equations have no solution, then what can we deduce? No fixed points, right? This is an inconsistent system of linear equations. So therefore we have no fixed points, and the isometry must be a glide reflection. So, no fixed points, since system of linear equations is not solvable. It implies glide reflection. Okay? Good. So, what else? What other questions should we go over together? Okay. That's fine. Then let's proceed our discussion about wallpaper groups. Okay. On Thursday of last week, I stated a theorem that I said we would prove first thing today. Let me remind you of what the statement of that theorem is. So, if a wallpaper group W contains a glide reflection then W has either rhombic or rectangular. Angular translation lattice. Okay. So just to recontextualize this, remember we're taking this broad general definition of wallpaper group, that it has a translation subgroup generated by two translations which share a common origin point and go to two other points which are non-collinear with A, right? We're taking that general definition of a wallpaper group and investigating what happens if we insist that our wallpaper group W contains an odd isometry, right? So the main thing we did on Thursday was prove that if a wallpaper group W contains a reflection, then either the line of that reflection is parallel to the diagonal of a rhombic unit cell, or W is parallel to the side of a rectangular unit cell. Okay, so this is saying a very similar thing, right? That say that if W contains a reflection, a translation lattice for W must be either rhombic or rectangular, right? Because the reflection, the line in which that reflection takes place, must be parallel to some component of a rhombic unit cell or a rectangular unit cell. Okay? So this is a weaker statement, right? Here, if W contains a glide reflection, we know that W possesses a translation lattice which is either rhombic or rectangular. We don't have any statement here about how the axis of this glide reflection relates to that rhombic or rectangular unit cell. It's a slightly weaker statement, but this is still very useful to us because we still have a nice to work with quadrilateral as the unit cell for our translation lattice for W. Okay? So, proof. So we'll suppose that gamma in W is a glide reflection with axis W. Okay? So, oh, I'm sorry, what do I say? Axis W. With axis L. Okay, now, so we can look back to our study of Friese groups, and we know the following. So we know that the smallest subgroup of our group W containing, I guess I should just say gamma here, containing gamma, and translations is the Friese group F13, which is just generated by gamma. Remember, this contains translations because the square of gamma is a translation, i.e., it's some power of tau. The translation that is a generator of F13, written in a different way, right? In fact, it's tau. Okay. So as we know this, so we suppose gamma squared is the shortest translation fixing L. Okay. Now, what I will do is take point A on L, and as per usual, our notation will let line A perpendicular And then let us set M equal to the image of A under gamma. Furthermore, we'll set, sorry, kind of wrote this in the wrong order. I don't know why. We'll also set P to be the image of A under gamma squared. And furthermore, we'll set capital P be equal to the image of capital A under gamma squared. Which, of course, implies that tau sub A comma P, the translation taking A to P, is the shortest translation, the shortest translation in F13, the group generated by gamma. Okay? So basically all I've done is fix some notation so I can write gamma squared based at some particular point, A. Okay? So now what we'll do is we'll let tau sub A comma B, A being the same initial point as we set for the initial point of tau, right? Is this point of intersection of L and some line perpendicular to it. Okay? So we'll let tau sub A comma B be the shortest translation in W, not in the group of translations generated by gamma squared. Okay, so hopefully this is starting to look kind of familiar, right? This is kind of a similar thing to what we did on Thursday, where we assume some translation is the shortest, and then take the shortest translation, which is not in the group generated by that shortest translation, and see what we can reason about. Okay, so we're doing a similar thing here. At this point, let me draw a picture of what's going on with all our notation here. Okay, so I start with this line A. Oh, well, actually, I started with my line L, right? The axis of the glide reflection. And then I chose line A to be the perpendicular line which intersects L at A. Okay, I set M to be the image of A under gamma, and I set line P equal to the image of line A under gamma squared. Right, so again, these are all perpendicular, and furthermore, they're equidistant from one another. Right, the directed distance from line A to M is the same as the directed distance from line M to P. And we named this point P. Right? Okay. So, since tau sub A comma P, or its inverse, times tau sub A comma B, we know that this cannot be shorter than tau sub A comma B, just by virtue of how we selected tau sub A comma B. Right. How we selected tau sub A comma B, the shortest translation in W, not in gamma squared, i.e. the group generated by tau sub A comma P. We know, we may suppose, I should say, we may suppose that B is either on line A or between A and line P. Okay? This is just like we talked about before, right? If I have point B here, and I were to do this pair of transformations in sequence, I go from A to B, and then say the translation from A to P is just gets me to this parallelogram, and this is tau sub A comma P. Sorry, it looks like B. I'm sorry. What am I saying here? What am I saying here? Suppose that either A is on, B is on A, or between A and B. Right. So what I need to say is, what goes wrong? Sorry for the confusion. What goes wrong if B is not on A or between A and P? Okay? Here's B. Okay, so translation from A to B. Translation from A to P. We translate this vector from A to P down to starting at B. So we get this parallelogram. Okay, so this point is tau sub A comma P times tau sub A comma B of point A, right? And I have that this length is less than the length of the translation tau sub A comma B, right? So therefore, we assume that A is between A and B, or perhaps on A. Okay? So, if first the case, if B is on A, right? Because if that's the case, W has a rectangular translation lattice. Has a rectangular translation lattice, and well, first of all, let's redraw our picture for this case, right? Okay. A, I'm gonna say B is here. Well, then our translation lattice is just defined by this rectangle, right? And in fact, so now I have to backtrack on what I said at the outset of this theorem, because even though we didn't state it in this way, we notice that L, the axis of the glide reflection, is parallel to a side of that translation lattice. And L is parallel to the side of a rectangular unit cell. Okay? So it actually is as nice as it can be. Okay? Now let's address the case if B is between A and P. Then let's let sigma sub L of B be equal to C. Well, then we must have the fact that the translation, which takes A to C, must be in W. And why is this? Since gamma times tau of A, tau sub A comma B, gamma inverse, is equal to gamma times tau sub A comma B of A sub negative 1 is equal to gamma of B sub negative 1, which is equal to C. Okay, so this demands some explanation, right? And as such, let me just use this diagram again. Okay, Okay, and I'll just erase the top part of the board. Remember, this is line L. Okay. So remember, okay, what we're assuming is that B is somewhere between A and P. Let's just say B is here. Okay? So if I do, oh, sorry. Also, I didn't evaluate this at A, right? I want to take this conjugation, gamma tau sub A comma B, gamma inverse, evaluated at A. What is A negative 1? Well, first of all, what does the glide reflection do? First of all, L is the axis of gamma, right? So it fixes the line gamma. But of course, it has no fixed points. It translates all the points on line gamma by whatever the translation component of gamma is, right? So that is to say, when we take gamma inverse of A, first I reflect in L, right, which leaves A fixed, and then I translate by the negative length of the translation component of gamma. So that is to say, this is my notation. A sub negative 1 is equal to gamma inverse of A. Right? After that, I do tau sub A comma B of A sub negative 1. Tau sub A comma B has translation vector that starts at A and points to B. So I move that vector down and base it at, sorry, that's not very good. I base it at A sub negative 1, right? So I went down, now I'm going this way to what I call B sub negative 1, which is tau sub A comma B of A sub negative 1. Okay? Now, I do gamma, which is, remember, what is a glide reflection? It's a translation followed by a reflection. And in our case, by our notation, it's a reflection in line L. Right? So I do the translation component of gamma, and I get up to B, and then I reflect B over line L to get to C, which is gamma of B sub negative 1. Okay? So just to reiterate, I drew this transformation from A to A sub negative 1 as a translation because the reflection component of gamma does not affect A. Right? It leaves it in the line L. Or rather, I should say, the reflection component fixes the point A. But then, of course, the translation component of the glide reflection gamma moves A along the line L. Okay? So, in any case, this verifies our claim that the translation, which takes A to C, is in our group W. And furthermore, translation taking A to C times the translation taking A to B is equal to gamma squared. How do I see that? You can tell me why that is. Well, let me ask you to verify this. Show that tau sub A comma C times tau sub A comma B is equal to gamma squared. Okay? This is a good exercise. Right. Okay, so do that tonight. But what does this tell us? If you haven't proved this for yourself already, which, it might take a minute, that's fine. But if we take this as fact, that this product of translations is equal to gamma squared, what does that tell us about B? Well, this implies then B must lie on line M. Right? That is to say, B must lie on M. Right? That is to say, remember, gamma squared takes A to P, right? A remains in the line L since gamma fixes the line L. And we're just doing the translational part of gamma twice, right? So we translate, we get to P. In order to go to C and then take this vector from A to B and get to P, we have to lie on the line M. That is, the reflection in line L of B must lie on M, which means B must lie on M. Okay? So, what do we have? Therefore, the quadrilateral A, B, P, C is a rhombic unit cell. Is a cell with L parallel to its diagonal. Okay, so in summary, the past two theorems that we proved show that if W contains an odd isometry, the translation lattice either has a rectangular or a rhombic unit cell. Okay, so in fact, we can say a little more about the wallpaper groups W, which contain a glide reflection. If that glide reflection treats the translation lattice nicely. What do I mean by nicely? Well, what I mean is that if a glide reflection fixes the translation lattice, not point-wise, mind you, because a glide reflection has no fixed points, but if it takes a point defining a translation lattice to another point in that translation lattice, then we can say more. Okay, so let me make that precise. Here's a theorem. If a glide reflection in wallpaper group W fixes a translation lattice for W, then W must contain a reflection. Okay, so notice in our last theorem, there was no assumption that there was a reflection in our wallpaper group W. Now, we're giving a condition on containing a glide reflection. If that glide reflection fixes a translation lattice for W, then W must also contain a reflection. Okay? So here's the proof. So let's say if glide reflection gamma takes point A to point P with point P in the translation lattice determined by A. Remember, there are many translation lattices for a given wallpaper group W, and they're all determined by some initial point A that we choose and evaluate all the translations contained in W at A. Right? So what I'm saying here is that P is equal to A sub ij for some I and j integers. Okay? Then, what we can say, then the translation taking A to P followed by gamma, oh I'm sorry, no, opposite order. Gamma followed by the translation taking A to P is a reflection. And how do I know that? Well, firstly, what is the parity of tau sub a comma p times gamma? Is it even or odd? Well, we know gamma is odd, right? And tau is a translation, so it's even. So therefore, we get an odd. Since it is odd, and furthermore, what if we evaluate tau sub a comma p times gamma at a? Well, we said that gamma takes a to p, right? So, oh, wait, I'm sorry. Oh, my goodness. Typo. I need to have these in the reverse order. Sorry. What we're really investigating is the translation taking p to a times gamma. P to a times gamma. And if we evaluate that at a, well, gamma of a is just p, so then we get tau sub p comma a of p equal to a. So in other words, a is a fixed point. So what do we know about odd isometries with fixed points that contain at least one fixed point? What are the odd isometries? Just reflections and glide reflections. Glide reflections have no fixed points. So by demonstrating that tau sub p comma a followed by gamma followed by tau sub p comma a has a fixed point, we know that it must in fact have a fixed line and be a reflection. Yes. So we know that tau sub p comma a times gamma is a reflection. Since it has at least one fixed point. Okay. So that does it for the preliminary results that we need about when a wallpaper group W contains an odd isometry. Aside from the translations, in addition to the translations. Now, let's examine what happens when W contains a rotation. Right? And of course, why don't I look at even isometries in general? Well, the only even isometries are translations and rotations. And the definition of a wallpaper group says that the subgroup of translations must be generated by 2 translations. So we're restricted in what translations can be contained by W. Therefore, the only remaining case is to see what happens when W contains a rotation. And this is the key result that we're now building up to, the key result that allows us to make the classification of wallpaper groups. And this is called the crystallographic restriction. Okay. So, why the word crystallographic? Well, it turns out we're able to significantly reduce the number of different rotations that we have to consider. And it has some historical connection with how crystallographers and mineralogists would classify the way gems would form in geometric shapes. Okay? So let's lay out some terminology. First of all, a point P is an end center for a group G of isometries if the rotations in G with center P form a cyclic group of order n. Of course, n will be strictly greater than 1 and finite. Okay, so that is to say, G has a finite cyclic subgroup Cn generated by, let me write this down. So in other notation, that is Cn generated by the rotation centered at P by 360 degrees divided by n. Okay, that's one way to write the cyclic subgroup with n elements. Is a subgroup of G. Okay. So, furthermore, I think we've kind of used this term in a loose fashion, but let's make it slightly more precise now. A figure is a non-empty subset, a non-empty set of points simply that. And if a figure has symmetry group with an end center, we'll call P. We also say the figure has end center P. Okay, so we're kind of conflating a figure with its symmetry group here, right? We define end center for a group, okay? But if there's a figure that has that group of isometries as its symmetry group, we can just as well say that the figure has an end center at P. Okay? And now, this is more a reminder than anything. We actually made this definition much earlier in the course. A center of symmetry is an end center for some integer n greater than 1. Okay? So that should seem familiar. Okay. Now, as it turns out, as I mentioned, we can, using this notion of an end center, we can severely reduce the number of rotations that we need to consider that can be added into a wallpaper group W. Okay? So here's our first simple theorem. For given n, strictly greater than 1, if point P is an end center for a group of isometries G and G contains an isometry taking P to Q, then you might suppose Q is also an end center of G. Okay? And in an entirely similar fashion, we can say that if L is a line of symmetry, if L is a line of symmetry for G, right, which of course means that G contains reflection in L as an isometry, then what can we say? If L is a line of symmetry for G, oh, I'm sorry, I should say, yeah, that's fine. And, sorry, that's a terrible G. And G contains an isometry taking L to M, some other line, then M is a line of symmetry of G as well. Okay, this should seem really familiar, right? Basically, it's essentially conjugation, right? This property that we've been using over and over again. Okay, so I'll do the first case. That is to say, when we have an n-centered P, and then I'll leave you the second case when we have a line of symmetry. Okay, it's exactly the same mechanically. Okay, so let's take an isometry alpha in G with alpha of P equal to Q. Then alpha rho sub P comma theta alpha to the -1 is just equal to rho sub alpha of P comma plus or minus theta, which of course is just rho sub Q plus or minus theta, which implies P is an n-center for G, if and only if Q is an n-center for G. Right, because if P is an n-center for G, what that's saying is if P is a n-center for G, then rho sub P of comma theta raised to the nth power is just the identity, iota. Now, where does this plus or minus come from? Well, that depends on if alpha is even or odd. However, rho sub Q, comma, plus or minus theta raised to the n power will also be iota, right? Because, well, let me just make a side note here. Since rho sub p comma theta raised to the n power is just rho sub p comma n times theta, right? Equal to iota. If and only if rho sub q, let's just assume that, for example, alpha was odd, then we would get rho sub q comma negative theta to the n is equal to rho sub q comma negative n theta, which is also just equal to iota, right? If n times theta is a multiple of 360, so will negative n times theta be a multiple of 360. And then we'll get iota again. Okay? So for homework, just quickly make the computation that verifies the second claim of this theorem. Prove the statement about lines of symmetry. And I hope that you see right away, you're going to use the same trick of conjugation that we have used tirelessly in the past 2 weeks. Okay, so now I'm going to prove something that's kind of surprising. That is to say, if rotations about two different centers are present in a wallpaper group W, then they must be a certain distance apart. Their centers must be a certain distance apart. Okay? Or rather, I guess the end result is that if you have two n centers in W, then those n centers cannot be too close together. Okay, and I'm going to make that more specific and precise now. So, here's the theorem. If rho sub A, comma, 360 divided by n, right? So I know A is an n center, and rho sub P, comma, 360 divided by n, P, another n center, and when I say another, what I mean is that A is not equal to P, and of course, n is greater than 1, let's say they're both in some wallpaper group W, then 2 times the distance from A to P is greater than or equal to the length non-identity, translation, in W. Okay? So, this is kind of important. Why is this? First we'll verify it, and then hopefully we'll start to see why it's important, and we'll definitely see more of that on Wednesday. But for now, here's the proof. So first, just by properties of W being a group, we know that W must contain rho sub p comma 360 divided by n times rho sub a comma 360 divided by n inverse. What's the inverse of a rotation? Well, I just negate the sine of the angle, right? So this is equivalent to rho sub p comma 360 divided by n times rho sub a comma negative 360 divided by n. Okay? And furthermore, by the angle addition theorem, what do we know? What does the angle addition theorem say? When we multiply two rotations together, what do we get? Anybody remember that? Well, let me remind you. What you get is a rotation about some new center by the sum of the angles of each of the rotations, unless they sum to a multiple of 360, i.e. 0 degrees. And in that case, what we get is a translation. So by the angle addition theorem, rho sub p comma 360 divided by n times rho sub a comma negative 360 divided by n must be a translation, a non-identity translation. This must be a non-identity translation. Which implies this product is of form tau 2 to the j, tau 1 to the I, for some I and j. Right? Where of course tau 1 and tau 2 are the translational generators for the translation subgroup of W. Okay, just like we've been talking about for wallpaper groups for the past 2 sessions. Okay? So we know a non-identity translation must be some product of a power of tau 2 times a power of tau 1. Okay, so combining our equations here, what do we get? We get rho sub p comma 360 divided by n times rho sub a, comma, 360 divided by n inverse is equal to tau 2 to the j, tau 1 to the I. If I rearrange this by multiplying on the right by tau sub a, comma, 360 divided by n, I get rho sub p, comma, 360 divided by n is equal to tau sub 2, comma, j, tau sub 1, comma, I, times rho sub a, comma, 360 divided by n. Right? Just multiplied by rho sub a, comma, 360 divided by n on both sides here. Okay. And evaluate on n, on a, and evaluate on point A. That is to say, I get rho sub p, comma, 360 divided by n of A is equal to tau sub 2 to the j, tau sub 1 to the I, rho sub a, comma, 360 divided by n of a. Well, rho sub a, comma, 360 divided by n fixes a because a is the center of rotation. So I get tau 2 to the j times tau 1 to the I of a, which is equal to a I j. Right? Okay, now there's just one special case here. If n is equal to 2, then what do we get? Then P is the midpoint of A and Aij, right? Because we see that rho sub P, comma, 360 divided by n takes A to A sub I, comma, j. Okay? So otherwise, n is greater than 2, and, by the triangle inequality, what do we get? We get AP plus P Aij, which of course is just 2 times AP, distance from A to P, is greater than or equal to the distance from A to Aij, which of course is positive, since we assume that tau sub 2 to the j and times tau sub 1 to the I is a non-identity translation. And so these are A and Aij are distinct points, so the distance between them is greater than 0. Let's just do a quick pictorial illustration here. So for n equals 2, what do we have? We have A, Aij, and here's our point P, and these two line segments have equal length. Now, if n is greater than 2, what do we have? We have this scenario. We have, here's our point P here. We have A and Aij. We get an isosceles triangle, right? Yeah? Okay, so that's where I invoke the triangle inequality, right? The fact that the sum of the lengths of these two sides necessarily must be larger than the third side, the length of the third side. Okay? Okay, so, therefore, 2 times the length from A to P is greater than or equal to, sorry, I should write this in words, is greater or equal to the length of any non-identity translation. In particular, the shortest non-identity translation. Okay? So, very quickly, the last thing we'll do today is just state 4 consequences of this theorem. Here are some consequences of this theorem. Okay, 1. No 2 end centers can be quote unquote too close. Okay? Furthermore, a 2 center and a 4 center, cannot be, again, too close. A 2 center and a 6 center cannot be too close. And for a 3 center and a 6 center cannot be too close. Okay. So, I'll give you some justification for these consequences tomorrow. Maybe just think about it tonight. I'm not asking you to do any rigorous justification. We'll say something about that. Actually, I guess that will be on Wednesday after the exam. And then I will go on to state the crystallographic restriction, which will allow us to at least start the classification of wallpaper groups. Okay? So, good luck studying tonight, and sometime this evening I'll post your grades for exam 3, and I'll see you all tomorrow, and have a good afternoon.